Today's lesson is on vector projections, and I'm going to start off with the warm-up. So we have a vector v with a magnitude of 8 going in the direction of vector u, and we want to just figure out what is the component form of v. So first thing you need to do is figure out what is the unit vector for u, because unit vectors allow us to capture the direction. So to do that, you need to figure out what the length of u is. So it's 3 squared plus 4 squared, which is 25, and the square root of that, which is 5. So the unit vector for u is going to be negative 3, 5, and 4, 5. So remember, a unit vector is just a vector with a length of 1 and just kind of captures the direction for us. If I want this unit vector to now have a length of 8 instead of 1, I just multiply it by 8. So I know v is just going to be 8 times that unit vector. So that's going to be negative 24 over 5 and 32 over 5. We do the exact same thing for this one. So I'm going to find its length, which is 13. I recognize this as a 5, 12, 13 triangle. So the unit vector is going to be 5 over 13 and 12 over 13. And I'll just multiply that by 8. So I'll get 40 over 13, and then I think 96 over 13. Okay, so that's what vector v equals. So my steps, pretty straightforward, I think. First thing I'm going to do is basically find the unit vector. I guess I should write words out here. Find the unit vector for the direction that we're trying to go in. And step B is I'm just going to multiply the new length that I want times that unit vector. And there you go. So this concept of vector projections is, it seems really complicated. It's actually not super complicated. So I'm going to start off by just drawing some random vector u. So I'm going to let that be right here. So this is vector u. And then I'm going to draw another vector, which is going to be v, and I'm going to purposely not draw it horizontal, okay? So I'm going to let that be vector v. And the projection of u onto v is kind of like if we had some sort of light source up here. So here's a nice happy little sun, and it was projecting its light down. What it would do is make a shadow. So u would cast a shadow onto v right here. And this is the projection vector of u onto v. Okay? So it's the projection of u onto v. So big letter u, little letter v, and that's how we write this notation here. And what this projection is the effective force of vector u in the direction of v. Okay? So it's basically how much force u can actually apply if it's going in that same direction as v. So there are a couple things that I want to point out about this projection and how we might find it, and some of the connections that we have going on here. So this light source, when it comes down, it forms a right angle with v, and so we have a right triangle here, and that angle right there, that's the angle in between u and v, and we have a formula for that. So we know that cosine theta is equal to the dot product over the magnitudes. So we can find this angle, the angle in between u and v. And in this setup right here, we can actually relate the projection, the length of u, so the length of the projection, the length of u, and this angle theta, because we know that cosine theta equals the adjacent side, so in this case that'll be the length of the projection, and the hypotenuse, which would be the length of u. So we can rewrite this and say we know that the length of the projection is going to equal the length of u times cosine theta, where cosine theta is the this value up here, or the angle in between. And we can use that to help us actually find this projection. Once we have the length of the projection, in order to actually find the component form of the projection vector, we just need to know what direction v is going in. And luckily for us, we know that if we can find the unit vector of v, that's going to capture the direction of v. And if we have the length of the projection, then we can just multiply those things together, and that will give us the actual projection of u onto v. So it all connects back to our warm-up, this two-step process. We need to have a length, and we need to have a unit vector. If we multiply those together, it will give us a new vector. To start off with, we'll go over example 1. So we're given a vector u is 6, 2, and vector v is 5, negative 5. And what we want to do is find this vector projection of u onto v. So in order to actually draw this, what I like to do is take this vector v, the vector that I'm actually going to be projecting onto, and I actually will rotate my paper so that it is parallel with me. Okay, so this is where I am, and it's going the same direction as me, and now it's very easy for me to start up here and drop a perpendicular line so that I can form a little right angle here. So I know that the vector projection of u onto v is going to be this little green vector right here. Okay, so I always just rotate my paper so that I can have this going in the horizontal direction. It makes it very easy to draw where the vector should be. Let's get my space back here. All right, so this is the projection of u onto v, and that's what we're trying to find. So we're going to do this in a two-step process as kind of described earlier, where I'm going to try to find the length of the projection, and then I'm going to find the direction of v. So that's what I'm going to start off with. So we'll say part 1 is find the length of the projection, and then part 2 will be find the unit vector of v. And we just multiply those together, and we're all done. Maybe easier said than done, but that's okay. I'm going to start off by reconnecting that this is both a triangle and this angle is the angle in between. So I'm going to start off by finding the angle in between. Okay, so using vector formulas. Cosine theta equals the dot product, okay, which remember is just the x values and the y values multiplied and then added together. So in this case, that's going to be 30 minus 10 over their magnitudes. So the length of this is 36 plus 4, so its magnitude is going to be the square root of 40. This guy's magnitude is going to be the square root of 50, which I could reduce. I'm not going to. So over here, back in this formula, just multiply those together. And now I could figure out what theta is if I wanted to, but I'm not going to bother, because next thing I'm going to do is use trig to set up the same ratio. So in this right triangle, I have theta, I have this is the length of this side, and over here I have the length of u. So I can set up that cosine theta has to equal the adjacent side, the length of the projection, over the hypotenuse, which is the length of u, which we found to be the square root of 40. And now looking at these, right here I have cosine theta equals something, and then cosine theta equals another thing. So since both of these are equal to cosine theta, I can set them equal to each other. So doing this allows me to solve for what the length of the projection would be. Okay, so I have 20 over, and I'm going to leave it not simplified still, so that you can kind of see what happens here, equals the length of the projection over the square root of 40. So this square root of 40 is going to cancel, and I now know that the length of the projection is going to be 20 over the square root of 50. Okay, and I could figure out what this is as decimal. I'm just not going to bother right this second. And that's the first part. We had to find the length of the projection. That's what it is. So part 2 is we need to find the unit vector of v. So we already know how to do that. Unit vector of v is just taking its current length and dividing each of its components. So 5 over the square root of 50. and negative 5 over the square root of 50. And again, we could simplify. I'm just not going to. And the reason I'm not going to is for this last step. So to find the actual projection, okay, of u onto v, we just multiply the length of the projection times that unit vector. So that's going to be 20 over the square root of 50 times this vector right here. Okay, so 5 over the square root of 50, negative 5 over the square root of 50. So I get 20 times 5, that's going to be 100, over square root of 50 times square root of 50, which is just 50. And then 20 times negative 5, so that's negative 100, over square root of 50, square root of 50. And I kind of ran out of room here, but this is going to become 2, and this is going to become negative 2. So that is what the projection of u onto v is in this situation. So we're going to try to summarize that, and we're going to come up with a formula that we can use. And I'm going to give you actually a couple different formulas that you might use in different situations, and then kind of tell you which one is the primary one that you'll use. So before we get to that, let's write those steps up of what we did. So the first thing we need to do was find the length of the projection. Okay, so in order for us to find the length of the projection, what we did first was we had to find the length of u and the length of v. And what we did next was we had to find the angle in between u and v. And we used trig then to actually find the length. Okay, so to just kind of summarize how that connected to what we just did up above, just to really remind you, we had that the cosine equaled the angle in between formula. And then we also recognized that it made a right triangle trig where we had the length of the projection divided by the length of u equaled cosine. So we set these things equal to each other. And we were able to simplify this down to say that the length of the projection would always be equal to the dot product over the length of v, and that's because the u's are going to cancel. Okay? All right, the second part was to find the unit vector of v. Okay, so that's what we wanted to do, find unit of v. And to do that, we actually just find the unit vector of v, right? We already know what its length is. So if I were to write this in formulas, we would have, let's just say v is a and b, just so I have some letters here. A divided by the length of the magnitude, and b divided by the length of the magnitude. So that would be what the unit vector is. That's by definition. And the last thing we would do then, okay, is we would multiply the length of the projection by that unit vector. Okay? So doing that in these formulas that we have going on here, the length of the projection is this dot product over the magnitude of v, and then we're multiplying that by a over the magnitude of v, comma, b over the magnitude of v, the unit vector. So to kind of make this formula a little bit nicer to work with, I'm going to factor out this on the bottom. So I'll actually end up having the magnitude of v squared. Okay, so the projection vector, so the actual vector, not its length or anything like that, is equal to the dot product of u and v over the magnitude of v squared, which some of you might remember is actually v dot v, if you wanted to write it that way. I wouldn't recommend. And then it would be times the vector a comma b, which is the vector v. So I can just write times vector v. So if you memorize this formula, you'll be able to find every single vector projection that you come across without really having to put in a lot of thought. You just find the dot product, divide it by the magnitude of v squared, and then just multiply that by the a and b value of vector v, and you're good to go. Now, all of my answer keys were set up to follow this 5-step process rather than using this formula. So for the rest of the packet, if you look at the answer key, that's how it's going to be solved. You're going to see me finding the length of u and v. You're going to see me finding the cosine value equaling the angle in between formula, then using trig to figure out what the length of the projection is, and then I'll multiply that by the unit vector, and I'll end up getting it. You could just do this. That's what I would recommend since we're learning this from home. If we were in school, I would probably be making you do the 5-step process because it really helps you understand what this projection is and where it's coming from. Now there's one last thing that I want to talk about before I actually erase any of this stuff and before we go on to the next stuff here, which is there's another way of thinking about what's going on here, okay? So we can actually say, if I rewrite this guy right here, okay, and I move this u over to the other side, I would have the length of the projection is equal to the length of u cosine theta. And the length of u, we often will just write that as the letter F, meaning that that's the force that we're exerting in a given direction, okay? So I can rewrite this as force cosine theta, where F is going to be the force in a direction, and theta is the angle in between that direction and which way you're kind of moving. So that connects back to the one I had on the other page where we had u and v. So we have u is going to be that actual force, and theta is going to be the angle in between u and v. So the reason I'm bringing this up right now is it's actually really useful in tomorrow's lesson. Okay, so it doesn't really do anything for us right now, but we're going to use that the length of the projection can be written as force cosine theta a lot in tomorrow's lesson. I'm going to do example number 2 with you as well, just because we get something kind of weird that actually happens if you were doing all of these in-between steps. So when we actually draw these two vectors out, which I'm not going to do for real here, but I have vector u is all the way over here, and then vector v is over this way. And it doesn't really work out too well for us when we're trying to figure out what's happening here, like which way is the projection actually pointing, because these vectors actually look like they're pointing in opposite directions. And the key here that we need to remember is that vectors don't need to be drawn from standard position. So we can actually move vector v from here and put it like this. And now we can drop this down, form our little right angle and all of our values here, and the projection would be right here, pointing in the opposite direction that v is actually pointing in, which is kind of neat. So if I follow all of these procedures here, and then I'll do the shortcut formula at the end for you to see that we get the same answers, I just want to show you something that's neat that happens with this length of the projection. So I'm going to find the length of u here. So it's 8 comma 5, so that's going to be the square root of 89. The length of v, that's going to be the square root of 85. I'm going to do cosine theta equals the dot product. Okay, so that's the x values plus the y values multiplied together, so it's negative 72 minus 10 over their lengths, square root of 89, square root of 85. And right here what I notice is this is a negative value, which makes sense if we think about where v actually is. This is an obtuse angle that's going to happen here, and that's theta, the angle in between right now. Next we'll do cosine theta equaling the trig values, so I'll have the length of the projection over the length of u, which is going to be the square root of 89. And so when I set these equal to each other, the length of the projection is going to equal a negative 82 over the square root of 85. So that's weird. We got a magnitude is negative, and so far we haven't had that with vectors. And it kind of doesn't work. Magnitudes aren't supposed to be negative, they're supposed to be positive. But you'll see actually when we get out of vectors and we move to the next chapter and the chapter after that one, that we kind of break that rule and we can actually think of this in a different way where it's okay that it's negative, and we'll be able to deal with that, particularly when we get to what's called polar. So that's what's interesting about this one. I just wanted to point that out, but the reason it's negative is because we need to reverse the direction ultimately. U is pointing in the opposite direction that V is pointing in, and this negative will take it from pointing this way to take it pointing that way. To finish this question up, I just need to find the unit vector of v, so that's going to be negative 9 over the square root of 85 and negative 2 over the square root of 85. And now I just multiply these things together, and I'm just going to use a calculator to do that. So I get 8.68 and 1.93, which we can see is in quadrant 1, which means it is pointing this way and not that way. Now if I use the formula that we developed at the end of the last one, it says that the projection of u unto v is equal to the dot product of u and v over the magnitude of v squared times vector v. So we can do that. The dot product is going to be negative 72 minus 10. Find the magnitude of v squared, we can come over here. It's a square root, so when we square it, it's just going to be 85, and then multiply that by vector v, which was negative 9 comma negative 2. So if we do this, negative 82 over 85, and we multiply that by negative 9 and then multiply it by negative 2, we should end up with the exact same thing, 8.68 and 1.93. So I would suggest, since we're doing this at home and not in school, that you use this formula because it's going to be very straightforward and easy for you. We just memorize dot product over v squared times v. Woo! That was so much fun, wasn't it?